Welcome to The Explainer. So today, we're unpacking a really fascinating PhD roadmap. It's designed to fundamentally change how billions of IoT devices communicate with one another, and crucially, do it without draining their precious batteries.
We're treating this highly technical research as a true innovator's quest. It's actually driven by this exact core philosophy from our source material. A PhD is about the lasting contribution of knowledge. This isn't just about passing a defense. It's about solving a massive, invisible problem that's currently holding back the entire Internet of Things.
Okay, let's dive into this roadmap. We're going to cover the IoT explosion and the TCP bottleneck, the PhD research quest, 5 steps to intelligent TCP, and finally, the ultimate integrated framework.
Part 1. The IoT explosion and the TCP bottleneck.
So, in a world of smart cities, connected healthcare, and literally billions of tiny devices, our current internet infrastructure is acting as a huge roadblock. Think about the protocol that runs most of the internet right now, traditional TCP. It was completely designed for wired, plugged-in computers. It requires this heavy, three-way handshake just to say hello, and it's constantly sending large headers and acknowledgments. It's basically like using a massive gas-guzzling delivery truck to do the job of a nimble, energy-efficient moped. It's just a total mismatch for our battery-powered, wirelessly constrained IoT devices.
Moving into Part 2, the PhD research quest.
To fix this gaping flaw, Dr. Bibudatta Sahu's research group at NIT Rourkela laid out a meticulously structured foundation. The logical flow of their opening chapter maps everything out perfectly. It takes us from the basic evolution of the internet and the nuts and bolts of IoT protocol stacks straight through to the glaring gaps in current TCP variants. It basically sets a rock-solid stage for an entirely new direction. And that brings us right to the first critical question of our quest. Why exactly does this heavyweight protocol fail so badly when put on tiny wireless sensors? Well, the source makes it pretty clear. IoT devices have super limited memory, extremely low computing power, and they rely on small batteries. So when TCP demands constant back and forth chatter just to keep a connection alive, it is literally draining the life out of these little sensors.
Section 3. 5 steps to intelligent TCP.
We can actually map out this progressive research evolution elegantly across a few core steps. First, simplify the connection to reduce overhead. Second, add intelligence to truly understand the cause of network errors. Third, heavily optimize the energy usage. And finally, collaborate using edge network context. Let's break down how the research tackles each of these one by one.
Step 1 is Lean TCP IoT, which acts as our foundation. The main goal here? Strip away that heavy connection establishment overhead. By using an adaptive handshake and reducing the header state, this proposed protocol drastically cuts down all that initial chatter. It allows resource-constrained devices to communicate efficiently, leaving all the bulky baggage of traditional TCP behind.
Okay, let's move to Step 2 and see how this builds. Step 2 adds the brains with IntelliLoss TCP. See, conventional TCP assumes that if a packet of data gets lost, there must be a traffic jam on the network, so it slows everything down and resends data. But in the IoT world, a lost packet often just means a wireless signal blipped out for a second because of interference. IntelliLoss uses machine learning to actually differentiate between a random wireless drop and true congestion. This is a game changer. It ensures your smart health monitor doesn't drain its battery resending data every single time a microwave turns on nearby.
The third step is eco-TCP IoT, which is all about optimizing energy. What's really amazing here is how it actively aligns the transport layer with the device's actual battery level and sleep schedules. It doesn't just blindly fire off data. It checks if the device needs to sleep to save power, creating this sustainable, long-term communication rhythm perfectly tailored for devices that might need to run for years on a single little coin battery.
Then we have Step 4, Edge TCP, which offloads the heavy lifting. Instead of forcing a tiny IoT sensor to figure everything out all on its own, it uses cross-layer feedback. It grabs data from the physical and network layers and uses an edge intelligence engine. Basically, this means the local network gateway, which actually has plugged-in power, steps up to help make smarter decisions for the tiny, battery-powered device. It vastly improves reliability.
Part 4. The ultimate integrated framework. Now, the absolutely crucial point here is how all these individual puzzle pieces merge into one grand solution. You can't just have one or the other. For true next-generation IoT, you need all of these optimizations working together in concert. Lean, IntelliLoss, Eco, and X-Edge seamlessly stack together into paper number 6 of this research journey, forming ILTCP IoT. It's a unified, self-optimizing framework that rolls lightweight architecture, AI, energy awareness, and edge computing into one single deployable package. To ground all this incredible theoretical work in reality, the roadmap provides a strict timeline. It represents the actual 6-semester project schedule. It systematically pulls us from a basic baseline study in mid-2026 through the progressive development of every single protocol we just talked about, all the way to a final thesis defense by June 2029.
When you look at the complete 6-semester Gantt chart, you see exactly how abstract concepts are turned into a structured, delivered reality over 3 years. Every algorithm design, every simulation in NS3, and every paper submission is perfectly mapped out. It really highlights the rigorous, step-by-step project management required to execute a complex PhD to this high of a standard.
As we wrap up this explainer, we have to return to the real-world impact. It's so clear that solving the internet's invisible bottlenecks, literally saving energy, bandwidth, and time at the microsecond level across billions of devices, is exactly what will make our future smart ecosystems possible. Without this foundational plumbing, the whole IoT revolution simply stalls out. Which leaves us with one final provocative thought. If researchers, like the team at NIT Rourkela, can make billions of tiny devices this incredibly intelligent and efficient, what massive global challenges will these invisible networks allow us to solve next? Thanks for exploring this fascinating roadmap with me, and keep questioning how the invisible systems around us actually work.